Hello. In today's video, I'm going to try and pull everything together from the other videos and show how everything works together to design an engine. Now, there's a playlist with videos, including videos from my other YouTube channel, on this website, on this YouTube channel. And there are, of course, other videos beyond that on the YouTube channel for the Cadillac group, which is my name plus Cadillac. And those are some other things you can draw on if I'm glazing over some of this a little bit too fast. But let's go over the basics of an engine. I am going to use a particular engine that we have. It's a 514 Cadillac motor. Now, I've used it in a lot of dyno testing. I call it the old war horse. We do a lot of changing around of what it does. It's basically a 514 flat top built Cadillac motor. Good rods, good pistons, reinforced bottom end. I've used this motor from 300 horsepower stock all the way up to 700 horsepower boosted. So I've used it for quite a bit. Now, it's basically going to be 10 to 1 if I run the Boogeyman heads, which is what I'm thinking about. If I run as cast Boogeyman heads with this motor, I wind up with 10 to 1 compression on a 514. So that head is 94 cc and a 225 valve. It basically flows between 340 and 360 CFM. Some of that, of course, depends on whether or not it's been ported and what valve lift we're talking about, because it does have more flow at a higher valve lift, but those valve lifts are sometimes a little hard to get to. In this case, I'm thinking we're going to talk more around 600 valve lift, which is pretty common for a lot of the motors that we do. The flow is really not the important part. The cross-section area is going to probably be my limiting factor. These heads have a bit of a problem with cross-section. The basic cross-section is 1,550 by 1,850, which is 2.87 square inches. Now, with porting, you can make it a little bigger, 1,600 by 1,950, and get a little bit more at the cross-section. Not a lot. There's not a lot of material in the casting. To truly go crazy, we'd either have to change the casting or weld it up and take out material. But in this case, we're just going to talk an as-cast head. So 2.87 square inches at the minimum cross-sectional area. And that's going to be my limiting factor. The higher flow of the head on the bench is immaterial, because I can't get there with this cross-sectional area. And it only shows up on the flow bench because you're only testing at about 320 feet per second. So it's an unrealistic number. This 287, if I use about 110 CFM per square inch, gives me 315.7 CFM. And that's probably a much more realistic number to be looking at as what we're going to be capable of doing. And the next question becomes with this, what RPM are we going to be working at? Now, remember, I did CFM demand, and part 2, I changed the formula after I learned some more about the formula. The new formula for CFM demand is substantially more accurate. I have now run it on a bunch of motors, and it is a much better choice. You really should be using this particular formula over the previous one. Now, if you remember correctly, this was airspeed and number of cylinders, and then of course half of the RPM and our CID to give me CFM. Now, in this case, I'm not really after CFM. I'm after RPM. So I have reconfigured it. Now, all I did was multiplied these bottom numbers together because I'm a V8. I tend to use V8s. That gives me 9824 as a constant for the bottom. And I could use this in the bottom instead of having to multiply these together. But I reconfigured the formula to look for RPM instead of CFM. And so it's 9824 times CFM divided by CID equals RPM. Now in the case of this motor, it's 514 CID, and we're using 300 and basically 16 CFM. And if I run that number out, it comes to about 6,000 RPM. So that's the neighborhood that this motor would be working in, giving the cubic inch displacement and the flow that we have available. And so that gives me an idea of where I should be sitting. So the next question is, what do I want to be doing in the way of power, and what do I want to do in the way of camshaft? Because that's the next piece of the puzzle. We're looking at 6,000 RPM. Now, as long as we're using the breathing, it will get there really kind of depending on any kind of cam. The cam, remember, is about how much fill we get, how much volumetric efficiency, and about the closing point, because we use inertia ram to figure out how much we're going to make. Now, in the case of the camshaft, I have a camshaft on the shelf that I'm really thinking about trying to use. It's a roller cam. It's 274, 268 at 50. Yes, it's a reverse split. It's on a 114 lobe center. And part of the reason for the reverse split is to reduce the overlap to see if I can not lose so much power down here. I still should have enough blowdown and exhaust to carry the motor, but we will have to see how it goes. The closing point is 71 degrees. Now remember, that has to do with inertia ram. Now this is a roller camshaft, so just to get a ballpark, I need to take 20 degrees out. If this was flat tappet, I'd be taking 25 degrees out. Now that's not a perfect number, but that gets us pretty close. And a lot of this, we're just trying to do plus or minus a little bit so that we know we're in the right ballpark when we go to run it. So if I do that, that would be 51 degrees, and that gives me a Z of 1.16. And so that's our target. That's our Z for the camshaft. So with a 1.16, that means I'm trying to fill the cylinder 16% past full. Volumetric efficiency of 116% or about there. And that's where I should be sitting. Now, the Z also affects the flow number because we're talking about the volume of air and the time. Remember, some of this is about time, the time for filling the cylinder. So if I take the 315, 316 CFM and I multiply it times 1.16, that gives me 366 CFM. And that is the number that I'm shooting for. If I take that number and try and figure out horsepower, I can do that. Because remember, horsepower is about CFM times 0.26, that number that Superflow came up with, times 8 cylinders, and in this case, times the Z. So we have 315.7 times 0.26 times 8 times 1.16, and that will give us horsepower. Now, that's the horsepower from the air. That gives us 762 horsepower. And so that's what we're kind of looking at. And then we have compression. So 10 to 1 compression, that's 2 points above 8 to 1. So that's going to add about 6% power. So that should put us right around 808 horsepower. So we're basically looking at an 800 horsepower motor with a 514, 10 to 1 Boogeyman heads, a flow of 315.7, and a camshaft that's 1.16 C. That's a big motor. That's a big horsepower motor. Now, the problem is not the peak. We should be able to generate the peak up there. The problem is this cam is big enough. What's going to happen down here? Do we wind up with just a really peaky motor that's really only good for race? Because for the most part, I do street strip, which is a little difficult. I mean, a lot of guys don't even like talking about it because you need drivability. You need it to work down here, and yet you still need it to have the horsepower to actually run down the track. And that's kind of what I'm looking at with this motor. So if this works, that would be the horsepower I'm going to make. And I know what you're saying. Well, are you sure that works? Because the question is, if I go through all this, do I actually make that horsepower, or is this just a dream? So I have a couple examples here. And these are all from testing we did with this same block with Richard Holdner years ago. And I chose these because I have data on them, but you can actually go look at the Richard Holdner videos or even talk to him, and that is what these motors are. So you have a way to verify what we did with these motors. Now, the first one I want to talk about is this one. This is a Bulldog intake with a 248 cam. Now that's a single plane intake, 248 flat tappet cam. So it's not a roller. It is fair size. The Z on this cam comes out to 0.92. So that will work out in what we're working on. The horsepower this motor did was 648 horsepower and 651 foot-pounds of torque. That's what it made when we ran it. If I calculate out, if I take out the 6% for the 10-to-1 compression, that makes it 611 horsepower from the airflow. So that comes out to 294 CFM from airflow. Now remember, this has a camshaft of 0.92. So if I divide 294 by 0.92, I get up 319 CFM. And that should be the CFM that I have in the headflow. And remember, up here, when we were looking with cross-section, that's basically what we have. 316 as opposed to 319. We're right in that ballpark for what we would expect to happen. And this particular motor went to 5,700 RPM, and if I calculate that out using CFM, that comes out to 298 CFM that it used to hit 57. And that's right in our same ballpark of where we're at on this particular motor. So you can see that the general scheme of what I'm using works in the real world. It is how engines generate power. That's why I say this is how it works, because I check this all the time against motors that actually run and produce power, because I should be able to predict, or otherwise the math is useless. So if we go on to the next run, we took the same motor, same intake, same block, same compression, same head, but we put in a bigger roller cam. We put in a 266 roller cam. That has a Z of 1.04. So it then made 722 horsepower instead of 648. And the foot-pounds stayed about the same, 652 compared to 651. Now remember, when I talked about torque, torque should be a flat number. In fact, the better you do in here with torque being flat, the better you are doing in how the engine runs. Because torque is really about the cubic inch displacement of the motor. So that makes sense that it was a good test. Now, if I take 722, take out the compression, that's 681 horsepower. And so if we take 681 horsepower and figure out how much CFM it took to generate that kind of horsepower, it's 327 CFM. And you're like, well, wait a minute, that's more than your 315. Well, remember, the camshaft is bigger. This camshaft is bigger than 1. We are filling the cylinder bigger than 100%. So again, you divide that in, and you come out to 315 CFM with the Z applied. And that's right back at the flow that we have on this motor. Now, you can also see that RPM jumped up to 6,500 RPM. Now, that figures out to a lot more CFM than we have. And we're not using all that CFM. So why are we at 6,500? Why did the RPM jump up? It's the same intake, it's the same motor, it's the same compression. The only thing that changed is the camshaft. And that's partly for 2 reasons. One, as you close this later and later, remember you need airspeed to be able to deal with this. And the main generator of airspeed is RPM. Now, remember in our inertial ram formula, it has to do with RPM, runner length, size of the valve, all of that. Now, most of those things didn't change. We didn't change the intake. The only thing we changed was the cam. But by closing that valve later and gaining that horsepower that we wanted, we were affecting the needed airspeed for the motor. So in order to do this one that's even bigger, we're really going to have to pay attention to airspeed. And airspeed is really about the intake manifold more than anything. So the question is, where are we sitting? We have run a motor with a similar cam. This is just a little bit bigger. This is 274, this was 266. So we're talking just a little bit bigger cam, a little bit later closing point on the valve. So what would we expect to happen? Well, we're probably okay at peak, but we may go up in RPM. Now, the question is, what happens with RPM? Because I said, with our CFM demand, we were going to peak at about 6,000. Now, we're in that neighborhood. This one is 5,700, but if you look, that comes out to just a little bit less CFM. Look, we're kind of in between these two. So the Z is somewhat affecting it because it's affecting the total flow. Now in this case, we're at the same CFM, but we're a little bit higher. Well, we're making better use of it. We're still right at about the CFM we should be. So we are not that far off at 5,700 RPM. At 65, we're probably getting a little more, but we are higher Z, and that is going to affect it. So one of the things I do is I went back and figured out runner length, because remember, part of inertial ram is not just flow, but it's about runner length. And I reconfigured the formula for inertial ram to solve for runner length. So we have the constant RPM divided by Z times the valve divided by the CID of one cylinder, because our inertial ram is really only talking about a single cylinder at a time. And if I take my new cam, it says I need a runner length of like 13.6 inches long. So that's not undoable, but that is long. Now, there's about 6.5 inches in the cylinder head. We have about a 6.5 inch of runner up to the flange. So that means I need about another 9 inches of runner length in the intake itself. Now, you would assume that the Bulldog intake, which is what we used on both of these runs, would be long enough. Because if you look at the intake, it has some runner length. But if you calculate 6,500 RPM, you come out to the only amount of runner it's using is 2.8 inches. Now remember, I told you taper will affect the intake manifold. It'll affect the runner length. It makes it appear shorter. So if you look at this intake, which I know it's going to be hard for you guys to see, but this has got a lot of taper and volume back here, but not in the last 2.8 inches. So it's really mostly using this much of the runner in order to work for inertia ramp. Now, we were trying to design a better version of this that wasn't quite so tapered, especially on these short runners. And unfortunately, Courtney passed away before we could get anywhere with that. But it goes to show you that an intake length can actually be altered with taper. So with 2.8 inches, what happens? What happens at 65? Is that where it peaks? Well, let me show you. Hopefully you can see this. This is this camshaft, 248 Zia .92, the one that made 648. Now, one of the things I wanted to point out is that's got that intake. That's got that same Bulldog intake. Why didn't it peak higher? Well, technically, it kind of did. I'm hoping you can see this, but if you look, it got flat. It basically peaked at 57, onesie twosie wide, but it carried all the way out to that 6,500 where the intake was tuned for. And so it really shows that it not only works on CFM demand, because it flattened out, it was done airwise, but the intake with airspeed wasn't quite done because it was tuned a little higher. And so that gave us our flat plane at the top. So if you go to a bigger camshaft, the question becomes what happens? And we have this one, which I said peaked at 6,500. Well, it did. And if you look on this particular one, it just came up and peaked. There's no flat. Well, that's because the bigger camshaft required more airspeed to be functional. The smaller camshaft had it and made it flat across the top. This one did not. This one just came up and peaked, and we lost horsepower down here. And that's because it's really designed to work at a higher RPM. That's where that intake is tuned for. With that runner and this size motor, it's really tuned to that 6,500 RPM. So what do we do in order to make it work better at a lower RPM? What other intake? I mean, I am somewhat limited with the Cadillac as to what intake I can run. I don't have, it's not like a small block where there's 100-something intakes where you can choose. This is really a limited number of options that I have. So what can we do? I mean, we could just run the Bulldog, but this is telling me, looking at that dyno sheet, that this motor is going to be pretty peaky. In racing, that might be okay. We could run 3,500 stall on it and run it up RPM wise, you know, shift at 68 and call it good, put some gear in it, and we'd be okay. But like I said, I'm street strip. I gotta kind of worry about down here. So what other intakes? Well, there's not a lot of choices. There is the Edelbrock intake. Now, we ran this same motor with the Edelbrock intake. Now, the Edelbrock intake is like most dual planes. It's dual plane, straight runner, longer, reduced plenum. This one has a Dominator adapter on it, but that's not a problem. And I have flow tested this particular intake. The runners, if you do all 8 runners, some of them flow about 290. Mostly you're 300 or just above. So on average, you have about 300 CFM of flow. So what does that do to our motor with the same cam? Because now we have the same cam on both of these motors, but different intakes. So if you look, this particular one with the Edelbrock peaked at the same RPM. Because like I said, that's really about the closing point of the intake and the airspeed that you have. And so I would have expected it to be the same, and it is. Now it made less horsepower by just a little bit. This made 630 horsepower as opposed to the Bulldog, which made 648. But if you look, torque was up. Now remember, torque is your indicator of how you're doing on airspeed. So we would expect that. That's why we use dual plane intakes. It ups the airspeed and it gives us more low-end power. And so that's what we're seeing here. It's not a big change, but it is a change. Now, that comes out to 594 horsepower from air, or about 285 CFM. So this engine with the Z is still in the neighborhood of what that is. But if you notice something, this is lower than that. Well, I told you, the intake when I flow test it, the average is probably about 300, right about there. It does a little better on these types of heads because it's a slightly raised runner. But it still is a flow in the runner of about 300 CFM. So that limited us just a little bit because we had 315 and we only used about 300 of it. And so you can see that the intake can be a restriction and it helps our airspeed, but then it'll hurt our horsepower because it's a restriction. It reduces the amount of flow we have. So to increase our airspeed, it's not like I can just put a way smaller intake on it. If I was to take an intake like this, which only flows about 160 CFM, and put it on those heads, there'd be no point. I'd be wasting most of the flow of the head. I might get a little more because there's going to be some cushion of air in the runner of the head, but it's really going to run this at max. Now my torque down here would be pretty good, but it'd fall off for a lack of airflow. It would peak early because my airflow would be down, so the RPM would be down. We'd make good torque, but we wouldn't make a lot of horsepower because we only have 160 CFM. So that doesn't really work. So the question becomes, what do we do in order to get both airspeed and airflow? And the real answer is runner length. And so the question becomes, what happens if we run something with a big runner length? This is the Acme intake. I know, it's crazy looking, isn't it? This was built years ago. Courtney has run a couple of these. I've had this one for a long time. I have never run it. And it might be worth trying on this to see what happens. Now this flows 360 CFM. So CFM wise, we have a cushion. Now, you don't necessarily want that either. You technically want, in a perfect world, to flow what the head flows and then the runner length that you need to make it work. And so this still isn't perfect. But what happens with too much cross-sectional area in the intake? Well, it can make it a little sluggish, but it also increases the RPM slightly that's required to hit an airspeed. Because remember, airspeed is about flow through a given cross-section. And so it may be okay. I wouldn't really know without testing it. But this runner length is long. This comes out with the runner length in the head of about 22 inches. So this thing is going to be tuned a lot lower RPM. And that could restrict us, because airspeed has a limit. Now, what Courtney told me when he ran these is he felt like it was running into fuel separation problems. And that would be an indication that you're maxing out the airspeed and not getting to where you should be by the airflow. And that's a real possibility. This could really do that, which means technically this would be too long. This would be too much motor for this kind of intake. And so I'm kind of stuck as to what intake to run. I don't really want to build a custom intake for this particular motor. Now, there are several other choices. I have shown the intake that I split in half, that I did dual quad, triple carburetors on. It runs really well. It made a fair amount of torque, so it has fairly decent airspeed with my modifications. It might be worth trying, but I don't really know where it sits in airspeed. It could also not support it well, because this is a much bigger cam than anything I ran in testing with that intake. I was thinking more along the lines of a street rod. Well, we also have a big, tall race intake. Now, the problem I have with it is I can't even measure how much it flows. It's beyond my bench. I think the intake flows in the neighborhood of 500 CFM a runner. I mean, it's got to be close to that, but that's big. And it has a big plenum. So down here, that's going to be a problem. That is not going to drive well at all. Now, it might make my peak power, but it's going to wind up with a very peaky motor. And I don't know if I can modify that intake to make it work. This particular intake, I wish I could just have one with straighter runners. I think it would behave itself much better with straighter runners. And I did kind of a sheet metal test of Courtney's that showed some promise. It needed to be probably a little bigger motor. We kind of had the motor toned down. It was iron head, and it might be worth trying, but it had some fuel distribution problems. The idea was to learn some to modify this intake. So you can see that given this information, I can kind of see, before I've even built the motor, where my problem is going to occur. And it looks like my main problem is going to be the flow and airspeed in the intake. And luckily the intake is fairly easy to swap around, so I could try a couple and see where I wind up. I can also custom build an intake, which I'd rather not do, or I'll have to come up with maybe another option. But by using the numbers and looking at the motor and knowing what cam I want to run. Now, I mean, my other choice, if I need to make it drivable, is not to run this much cam. But I kind of would like to hit that number. But I'd like to hit that number and still have low end torque. So I'm asking a lot. That's part of the reason I chose this particular exercise, is it goes to show that sometimes it's not easy to get everything you want and make the motor behave the way you want it to behave. And so these are the things you need to look at, and you can see that this math that I've been trying to show in these previous videos, it works. It is how the motor works. So we have a good handle on how the engine will actually behave, and we just need to pick the appropriate parts that will work for us and make that happen. So I hope this exercise kind of helps you and gets you to where you need to go. And I wish you well on all your projects. And I also wish you a Merry Christmas, since this is Christmas. And I hope you do well in the next year. And I hope you do well at making horsepower. And I hope all of this helps, because I feel like it does wonders for me knowing where I'm sitting. Talk to you later. Bye.